What if I told you that the most dominant racing transmission in drag racing history wasn't built by engineers in $1 million lab, wasn't developed by a factory-backed team with unlimited resources, and wasn't even designed for performance? What if I told you it was a 2-speed economy box that Chevrolet literally built for your grandmother's grocery getter, and that one obsessive, permanently irritated racer from Pennsylvania used it to humiliate every factory team in the country and reset the record books so many times that GM's own engineers eventually had to sit down and admit they'd been wrong for 20 years? That's not a hypothetical. That actually happened. And the man who made it happen did it with a transmission everyone else was literally throwing in the junkyard. This is legacy motoring, and I spend way too much time thinking about the engineering decisions that changed motorsports forever. If you're someone who loves the deep technical stories behind drag racing's greatest upsets and wants to understand why the underdogs sometimes rewrite history, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Alright, let's set the scene properly, because context matters here and the contrast is everything. It's a Saturday night at National Trail Raceway in Ohio. The year is 1970. The air smells like burned rubber, nitromethane, and money, because there is a lot of money in these pits. You've got factory-backed teams from Chrysler rolling in with semi-trailers full of spare parts. You've got Ford engineers in polo shirts writing things on clipboard. You've got Dodge spending what would be the equivalent of tens of millions of dollars in today's money trying to dominate the pro stock class. These are professional operations with dyno rooms, computer modeling, and teams of engineers who went to actual universities and studied actual physics. And then Bill Jenkins shows up. He drives his own rig. He wrenches his own car. He has the approximate social warmth of a parking ticket, which is how he earned the nickname Grumpy, and he has a 1970 Vega that looks vaguely suspicious to anyone who knows what they're looking at. The tech inspectors crouch down, look under the car, and they see something that genuinely makes them do a double take. Not a turbo-hydromatic 400. Not a close-ratio 4-speed manual. Not anything that any performance engineer in the country would ever spec for a race car. What they see is a Powerglide. A 2-speed automatic transmission that Chevrolet designed in 1950 for 6-cylinder sedans driven by people who thought driving was a chore rather than a hobby. The same transmission that came bolted behind the engine in base model Impalas bought by suburban commuters who wanted their car to be as boring and effortless as possible. The laughter in the pit lane is real. Veteran racers, experienced crew chiefs, guys who have forgotten more about drag racing than most people ever learn, they're all pointing and cracking jokes. The Powerglide. In pro stock, this grumpy lunatic has officially lost his mind. By the end of the night, nobody is laughing. Jenkins just ran 8.6 seconds flat and reset the pro stock elapsed time record. The cheapest, weakest, most dismissively ordinary automatic transmission Chevrolet ever bolted into a production car just beat every single piece of sophisticated engineering those factory teams had spent fortunes developing. And here's the thing that makes this story so much more than just a fun drag racing anecdote. Jenkins didn't get lucky. He didn't stumble onto a freak combination that happened to work once on a cool night with a tailwind. He had done the math. He had run the calculations. He had systematically dismantled 50 years of automotive engineering dogma using nothing but a stopwatch, a slide rule, and a willingness to question assumptions that everyone else treated as settled law. The Powerglide wasn't supposed to be fast. It was never marketed for performance. Chevrolet's own engineers actively steered racers away from it. But Jenkins had seen something in the numbers that nobody else had bothered to look for, and once he found it, drag racing would never be the same again. To understand why Jenkins's Powerglide discovery was so genuinely radical, you have to understand the world it emerged from, and that means going back to 1950. General Motors was under pressure to develop a competitive automatic transmission. Ford had found success with their automatic offerings, and GM needed an answer. The engineering brief for the Powerglide was straightforward and completely unambiguous about its priorities. Cheap to manufacture, smooth for everyday comfort, reliable enough for ordinary use. Performance was not on the list. It wasn't an afterthought. It was not even mentioned. The transmission was a business decision dressed up in engineering, designed to move units in showrooms, not move race cars down drag strip. The two-speed design used a simple planetary gear set paired with a torque converter. First gear gave you a 1.76-to-1 ratio. Second gear was direct drive at 1-to-1. That was the entire transmission. No overdrive. No complex electronic. No multiple clutch packs working in elaborate sequences. Just 2 gears and a torque converter, and in terms of sheer mechanical ambition, it was about as exciting as a butter knife. Meanwhile, Chevrolet's actual performance flagship was the Turbo-Hydromatic 400. Introduced in 1964, the TH400 was genuinely impressive engineering. 3 forward speeds with ratios of 2.48-to-1, 1.48-to-1, and direct drive. It could handle 450 pound-feet of torque in stock trim. The transmission had multiple clutch packs, a complex valve body with sophisticated hydraulic logic, and weighed 135 pounds dry. Racing teams loved it because it was essentially bulletproof. Funny car teams were routinely pushing 2,000 horsepower through modified TH400s, and the things just kept working. The Powerglide, by comparison, weighed 95 pounds and was rated for around 300 horsepower on an optimistic day. Chevrolet's own engineers recommended it exclusively for 6-cylinder applications and small-block V8s, making under 300 horsepower. In the context of professional drag racing, the Powerglide wasn't just considered inadequate. It was considered irrelevant. Now, you might be thinking, if the TH400 was so obviously superior in every measurable specification, how on earth did Jenkins even arrive at the idea that the Powerglide might be faster? That's exactly the right question, and the answer reveals something genuinely brilliant about the way Jenkins thought about problems. By 1969, Pro Stock was the hottest class in drag racing and the most intensely contested. Factory-backed programs from Chrysler, Ford, and GM were spending millions. The rules required stock-appearing bodies and production-based engines, but within those constraints, everything else was a legitimate engineering exercise. Teams were running trick 4-speed manuals with lightning-fast shifters or heavily modified TH400s equipped with transbrakes and high-stall converters. The racing gospel of that era was unified and confident. More gears equal faster elapsed times. First gear multiplication launches you off the line. Second gear keeps the engine in its power band through mid-track. Third gear carries you through the trap. Every performance manual published between 1960 and 1970 said the same thing. Every racing consultant, every factory engineer, every experienced crew chief agreed. More gears meant more opportunities to keep the engine singing in its optimal RPM range, and keeping the engine in its power band was everything. Enter Jenkins, 6'2", permanently scowling, and constitutionally incapable of accepting received wisdom without first stress-testing it against actual data. They called him grumpy because he had the social temperament of a cactus and roughly as much patience for unexamined assumptions. Jenkins ran a modest 2-bay garage and built engines for local racers, but what set him apart from the rest of the field wasn't cubic inches or budget. It was an almost pathological obsession with efficiency. While Ford and Chrysler were throwing displacement at the problem, Jenkins was in his shop with a slide rule, calculating losses. Here's what most people don't realize about the conventional wisdom Jenkins was challenging. Everyone was focused on keeping engines in their power band, which sounds completely reasonable, but nobody was calculating the cost of the shifts themselves. Every time an automatic transmission shifts, there is a power interruption. The engine must drop RPM. The transmission must release one clutch pack and engage another. The drivetrain must absorb the resulting shock and resume acceleration. In a TH400, you're doing this twice. Once from first to second at roughly 1.2 seconds into the run. Once from second to third at around 3.5 seconds. Jenkins's calculation showed that each of those shifts was costing approximately 0.2 of a second. Not in the mechanical shift time itself. The TH400 could bang gears in around 300 milliseconds. The loss came from power interruption and drivetrain shock absorption. Jenkins's theory was elegant in its simplicity. Eliminate one shift. Eliminate one power interruption. The Powerglide would shift once, at approximately 2.8 seconds into the run, and then pull all the way to the finish line in high gear. Less complexity. Less rotating mass. One decisive mechanical event instead of two. The math pointed clearly in one direction. He started testing with a borrowed Powerglide in late 1969, and the first tests were catastrophic. The stock transmission exploded on the third pass. The aluminum case split open like a stressed-out beer can. The planetary gear set disintegrated into shrapnel, and Jenkins spent 2 hours with a magnet picking transmission components out of the oil pan. Most people would have taken that as a fairly unambiguous message from the universe. Jenkins looked at the data from those 3 runs and noticed something. Before the transmission grenade itself, the car was posting 60 foot times identical to his TH400 test mule. But it was gaining 2 car lengths by half-track. The theory was completely sound. The execution needed serious work. Jenkins went after the Powerglide's weaknesses with the same systematic intensity he applied to everything else. The stock aluminum case was replaced with a modified cast iron unit sourced from a 1962 Corvette. Stronger, heavier in absolute terms, but Jenkins wasn't chasing weight savings with the case. He was chasing survival. The planetary gear set got completely replaced with heat-treated 4,140 steel components machined to much tighter tolerances than anything GM had ever considered for a transmission designed to shift gently into second gear on the way to the grocery store. The torque converter was where Jenkins made one of his most important decisions. Stock Powerglide converters were 11-inch units designed around the priorities of smooth engagement and comfortable driving. They would slip 15 to 20% under full power, converting enormous amounts of energy into heat rather than wheel torque. Jenkins worked with ATI to develop a custom 10-inch converter with a 5,000 revolutions per minute stall speed. Smaller diameter meant faster RPM response. The higher stall speed meant the engine could build power before the drivetrain loaded up, and the tighter internal clearances meant far less slippage once the converter locked into coupling range. The valve body received a complete recalibration for a single purpose. Lightning-quick, precisely timed shifts at exactly 7,200 revolutions per minute, regardless of throttle position, regardless of road speed, regardless of anything except the single number Jenkins had calculated as the optimal shift point for his engine combination. No hunting for the right gear. No governor-based guesswork. One number. One shift. Done. The weak link that nearly derailed the entire project was the input shaft. The stock Powerglide used a relatively modest piece of 1020 steel that was perfectly adequate for the loads it was designed to handle and completely inadequate for what Jenkins was asking of it. Under 650 horsepower with a 5,000 revolutions per minute stall converter hammering torque pulses into it at launch, the stock shaft twisted and eventually failed. Jenkins had Summers Brothers machine him billet 300M steel shafts that were 40% larger in diameter. The material selection alone was remarkable. 300M is an ultra-high-strength steel alloy developed for aircraft landing gear, capable of handling extraordinary stress concentrations without fracturing. Jenkins was using aerospace materials in a transmission that Chevrolet originally equipped with components adequate for a family sedan. But here's where it gets really interesting. because there was an advantage hiding inside the Powerglide's simple design that nobody had quantified before Jenkins started digging into the numbers. The TH400 used a Simpson planetary gear set. This is a complex arrangement involving multiple sun gears, planet carriers, and ring gears working in coordinated sequences. In first gear, the power path through the TH400 runs through two separate planetary sets. That means more total rotating mass, more bearing surfaces generating friction, more components that need to accelerate from rest every single run. The Powerglide used a Ravigno's gear set. One sun gear, one planet carrier, one ring gear. The power path was dramatically more direct. Jenkins calculated that the Powerglide had 18% less rotating mass than the TH400 in race trim. In drag racing, rotating mass is one of your fundamental enemies. Every pound of rotating weight requires horsepower to accelerate, and it requires it constantly, throughout the entire run. A pound of rotating weight at the transmission output shaft is approximately 8 times as costly in performance terms as a pound of static weight sitting in the trunk. Jenkins was removing the equivalent of nearly 380 pounds of static weight simply by choosing the Powerglide over the TH400, before accounting for the actual 40-pound weight difference between the two transmissions. The rebuilt Powerglide went into Jenkins's 1970 Vega Pro stock car in March of that year. The car itself was already unconventional by the standards of the day. Full-tube chassis narrowed 3 inches, all-steel body, and a destroked 331 cubic inch small block Chevrolet that was spun to 9,500 revolutions per minute. While every other serious pro stock competitor was running 430 to 450 cubic inch big blocks, Jenkins was giving away 100 cubic inches of displacement. He was compensating with 180 pounds less weight and a drivetrain optimized for efficiency rather than brute force. The first race with the rebuilt combination was the Gator Nationals. Jenkins qualified third, ran consistent 9.90s, and lost in the semi-finals to Ronnie Sox's Hemis, which was a perfectly respectable result against one of the most talented drivers in the sport with a factory-backed program behind him. But people in the pits were noticing something that didn't quite add up. Jenkins was crossing the finish line at lower RPM than any other car in the field. Yet his trap speeds were identical to the big block cars. Observant crew chiefs were working the math on their clipboards and getting numbers that didn't fit their understanding of how transmissions worked. Here was what they were seeing but not yet fully understanding. The Powerglide was pulling from 5,000 revolutions per minute all the way to 8,500 revolutions per minute in high gear. A 3,500 revolutions per minute operating window in the top ratio. The TH400 cars were shifting into third gear at 7,200 revolutions per minute and pulling to 8,200. A 1,000 revolutions per minute window before crossing the line. Jenkins's engine was accelerating for a much longer period in each gear, and the single-shift architecture meant that the car never experienced the momentum disruption of a second power interruption at the worst possible moment in the run. By June, Jenkins had the combination fully sorted. The Powerglide was shifting at exactly 1.95 seconds into the run at 7,400 revolutions per minute, then pulling clean to 8,800 revolutions per minute at the stripe. The car was running 9.60s at 142 miles per hour. At the Summer Nationals, he drew Dick Landy's factory-backed Dodge Challenger in a round that should, by any conventional analysis, have been a relatively easy win for the Mopar. Landy's 440 wedge engine displaced nearly 100 more cubic inches. His TH727 3-speed was perfectly calibrated. Landy himself was one of the most experienced and technically sophisticated racers in the class. They left the line together. Jenkins pulled a fender at 60 feet, which was unexpected given the cubic inch deficit. By the time Landy's 727 shifted into third gear, Jenkins was already gone. The Vega won by 3 car lengths. The Powerglide had announced itself. Now here's the kicker, and this detail tells you everything about how significant that run was. Chrysler engineers were in the stands that day. They had data acquisition equipment. They were there to monitor Landy's performance data and look for areas to optimize. When they pulled Jenkins's time slips and cross-referenced them against their own data, they ran the numbers 3 times because the conclusion seemed impossible. Jenkins was posting identical 60-foot times to Landy, 1.29 seconds, meaning both cars were getting off the line with equal efficiency. Both cars were making approximately 650 horsepower. But Jenkins was consistently running 20 to 30 hundredths of a second quicker to the finish line. The Chrysler engineers' conclusion was clear. The Powerglide's single-shift architecture was saving more time than the TH727's gear multiplication advantage could overcome over the course of a quarter-mile run. The math they'd been using for 20 years was missing a variable, and Bill Jenkins had just demonstrated that variable in front of 40,000 spectators. Word moved through the pits at the speed of rumor, which in a drag racing paddock is approximately the speed of sound. Jenkins tried to keep the Powerglide configuration secret. He went so far as to fabricate a fake TH400 oil pan to bolt on for tech inspection, a piece of misdirection that bought him exactly as long as it took for other teams' crew chiefs to start noticing that the transmission cooler lines were in the wrong location. The shifter only had 2 meaningful forward positions, and the car made a distinctive high-pitched whine at launch that no TH400 ever produced. By September of 1970, the secret was completely out. Bill Jenkins was beating million-dollar factory programs with a transmission that had been collecting dust in junkyards across America. The physics behind Jenkins's success deserve a careful explanation, because this is where the story moves from being an interesting racing anecdote to being a legitimate lesson in engineering methodology. In a theoretical perfect world, keeping an engine at its peak power output throughout an entire acceleration run would yield the fastest possible elapsed time. This is the logic behind Formula One's 8 and 9-speed gearboxes. Keep the engine singing in the narrow band where it makes maximum power, and let the transmission handle all the ratio changes needed to maintain that. But a quarter-mile drag race is not Formula One. You're accelerating from a dead stop to 150 miles per hour in under 10 seconds. The run is over before most turbocharged passenger cars have fully spooled. Every millisecond genuinely matters, and the costs of complexity are paid in real time, every single run. The TH400's first to second shift happened at roughly 55 miles per hour. Second to third occurred around 95 miles per hour. Each shift required releasing one set of clutch packs and applying another. Even with the most precise preparation and the most aggressive valve body calibration available, you're looking at 300 milliseconds per shift, during which zero driving force reaches the rear wheels. Multiply that across 2 shifts, and you've spent 600 milliseconds of your approximately 9,500 millisecond run doing nothing useful. The Powerglide shifted once at around 75 miles per hour. 1 interruption instead of 2. But the rotating mass calculation was where Jenkins's analysis delivered its most surprising insight. And this is the part that even experienced racers of the era hadn't fully accounted for in their thinking. The TH400's Simpson planetary arrangement, with its 2 interconnected gear sets working in sequence, created a combined rotating assembly that Jenkins's measurements put at 18% heavier than the Powerglide's single Ravigno's set. That number sounds abstract until you apply the physics of rotational inertia to a drag racing context. Here's a useful way to think about it. When a drag car launches, the engine isn't just pushing the car forward. It's simultaneously accelerating every rotating component in the drivetrain from rest up to operating speed. The crankshaft, the flywheel or flex plate, the torque converter, the transmission's internal rotating assembly, the drive shaft, the rear axle, the wheels and tires. Every one of those components requires energy to spin up. The energy required to accelerate a rotating mass is proportional to the mass and to the square of the radius at which that mass is distributed. This means that rotating weight is disproportionately expensive compared to static weight. Engineering convention in drag racing uses a multiplier of approximately 8 to 1 for rotating versus static mass in practical performance terms. Jenkins calculated that the Powerglide's reduced rotating assembly was equivalent to removing roughly 376 pounds of static weight from the car. In pro stock, where teams fight over every half-pound of ballast placement, that number is staggering. And unlike actual weight removal, which requires either removing material from the car itself or finding lighter components, this advantage was essentially free once the Powerglide was proven to survive under race conditions. The torque converter efficiency story added another layer. Jenkins's custom 10-inch, 5,000 revolutions per minute stall unit demonstrated coupling efficiency above 97% once the engine exceeded 5,500 revolutions per minute. The stock converter Jenkins started with, and the conventional high-performance TH400 converters his competitors were running, both showed measurable slippage well into the higher RPM range. Every percent of converter slippage is a direct energy loss, converting crankshaft power into heat in the transmission fluid rather than into wheel torque. Jenkins estimated his converter was delivering approximately 8% more power to the rear wheels than comparable TH400 setups at speeds above 100 miles per hour. In a 9.5-second race, 8% more power in the second half of the run translates directly and substantially into elapsed time improvement. The gear ratio spread told a complementary story. The TH400's ratios created significant RPM drops at each shift. First to second was a 40% RPM drop. Second to third was a 32% drop. After each shift, the engine had to rebuild from the lower RPM point back up through its power band. The Powerglide's single shift from 1.76 to 1.0 was a 43% drop, which sounds worse, but it happened once. And critically, Jenkins had engineered his engine specifically around this shift architecture. Peak torque arrived at 6,200 revolutions per minute. Peak power at 8,200 revolutions per minute. The engine's power curve was shaped to work in concert with the Powerglide's operating window, not the other way around. The transmission and engine were designed as an integrated system rather than as separate components that happened to be bolted together. This is where the modification work becomes genuinely impressive engineering rather than just parts swapping. Jenkins had to compensate for the Powerglide's lower first-gear ratio compared to the TH400. Where TH400 cars were running 4.10 to 1 or 4.30 to 1 rear axle gearing, Jenkins bolted in 5.13 to 1 or even 5.38 to 1 ratios. The final drive multiplication worked out similarly between the two setups, but now Jenkins had the advantage of one less shift, one less rotating gear set, and a torque converter that was coupling more efficiently at the speeds where races are won. Let's talk specifically about what Jenkins did to make the Powerglide survive loads it was never designed to see, because the survival story is as technically interesting as the performance story. The clutch pack redesign was fundamental. Stock Powerglides used 4 friction discs in the high-gear clutch assembly. The friction material was a relatively soft organic compound chosen for smooth, quiet engagement on light-duty applications. Jenkins rebuilt the high-gear clutch with 9 alternating discs using carbon fiber friction material. The apply pistons that pressed the clutch pack together were completely replaced. The factory pistons included cushion springs designed to ease engagement gradually, producing the smooth shifts that suburban drivers expected. Jenkins machined solid aluminum pistons with no cushioning whatsoever. The resulting shifts were described by everyone who rode in the car as violent enough to leave bruises. But they were consistent, instantaneous, and absolutely decisive. The clutch was either fully released or fully applied. No slipping, no intermediate state, no power loss during the engagement process. The valve bodywork was performed by Tom Williams at Tom's Transmission in what became a 3-month exercise in hydraulic precision. Stock Powerglides relied on a mechanical governor system using flyweights and calibrated springs to determine shift timing based on road speed. Jenkins wanted nothing to do with a system that had any mechanical variability. Williams installed a transbrake valve that locked the first gear and reverse clutch packs simultaneously for staging, creating a solid drivetrain that could build full engine power against before launch. When Jenkins released the transbrake, the car launched with the full force of an engine already at 5,000 plus RPM rather than having to build from idle. The upshift was controlled by a Hobbs pressure switch monitoring engine oil pressure. At exactly 95 psi, which corresponded precisely to 7,400 revolutions per minute in Jenkins's engine, the transmission shifted. Not approximately 7,400 revolutions per minute. Exactly 7,400 revolutions per minute, every single run, regardless of temperature, regardless of track conditions, regardless of how Jenkins was feeling about his day. The consistency this produced was measurable and meaningful. While TH400 cars might vary by 30/100ths of a second run to run depending on shift quality, Jenkins's Powerglide setup varied by less than 100. In a class where the difference between winning and losing was often measured in hundredths, that consistency was worth real money. The 1970 season finale at the World Finals in Dallas put everything on display. Jenkins drew Ronnie Sox's Hemis in the final round. Sox was universally regarded as the most talented driver in pro stock. His Chrysler program had factory backing and essentially unlimited resources. The Hemi engine in Sox's car was producing 675 horsepower. Jenkins's destroked 331 cubic inch small block was making approximately 650, despite having nearly 100 fewer cubic inches to work with. Vegas had Sox favored at 3-1. Jenkins had other plans. The tree dropped. Jenkins cut a light measured at exactly 500 milliseconds, a reaction time that was essentially perfect for the era. The Vega pulled a fender at 60 feet. Sox's Hemi was screaming through the gears, but every time the TH727 shifted, the momentum interruption was visible on the time slip and felt in the finish line gap. The Powerglide shifted once at the 330-foot mark, then pulled clean and hard all the way to the stripe. Jenkins crossed at 8.62 seconds and 158.43 miles per hour, a new pro stock national record. Sox was 20 hundredths behind. The crowd was stunned. The Powerglide had not just won. It had won while setting a record that nobody in the field had come close to before. The morning after that final, Jenkins's phone started ringing before sunrise and didn't stop for 3 days. Every serious racer in the country wanted a Powerglide. Transmission shops that had been routinely tossing Powerglides in the scrap pile suddenly had customers calling from 7 states away asking if they had any in stock. The problem was immediate and significant. GM had discontinued Powerglide production for performance applications in 1972. The only supply was the junkyard market, and those dried up with startling speed. A transmission that had been sitting in wrecking yards for $50 changed hands for $500 within months. Some clean, low-mileage examples brought over $800. Chevrolet's economy transmission had become genuinely rare in the exact moment it became genuinely desirable. But Jenkins's impact extended well beyond the immediate scramble for hardware. His success forced a systematic rethinking of transmission theory throughout the entire sport. Don Nicholson began testing a Powerglide installation in his pro stock Maverick almost immediately. He recognized that the Ford C4 transmission was architecturally similar, a 2-speed unit with a simple design philosophy, and began applying Jenkins's principles to the Ford platform. Nicholson started winning. Chrysler's engineers, those same engineers who had watched their computerized analysis confirm Jenkins's advantage from the stands at the Summer Nationals, began developing a dedicated two-speed version of the TorqueFlite specifically for drag racing applications. Within 2 seasons, approximately half the pro stock field had abandoned the 3-speed philosophy entirely. General Motors' institutional response to Jenkins's success is one of the more fascinating organizational stories in racing history, because it puts a large corporation in the position of having to quietly acknowledge that one of its most celebrated performance products had just been defeated by one of its cheapest economy products, in front of a national audience, repeatedly. GM engineers had spent considerable money and considerable pride promoting the TH400 as the ultimate expression of automatic transmission performance. Their advertising called it the choice of champions. Their engineering documentation supported it with data. Their sales materials pushed it to performance buyers as the obvious and correct choice. Now, one garage racer from Pennsylvania was demonstrating, run after run, that their economy transmission was faster. The cognitive dissonance must have been significant. Engineers from GM's Hydromatic division visited Jenkins's shop. They examined the Powerglide installation. They studied his torque converter specifications, his valve body calibration, his gear ratio selection, and his rotating mass calculations. And they couldn't argue with any of it. The physics were unambiguous. Jenkins had found a real optimization that GM's own development process had missed, not because GM's engineers were incompetent, but because nobody in the corporate program had been asking whether fewer gears might outperform more gears in the specific context of a quarter-mile race. That question violated too many assumptions to seem worth asking. In 1971, GM quietly began offering a heavy-duty Powerglide option for Camaros and Novas ordered through the Central Office Production Order System, the COPO program that had already been used to deliver factory-built race vehicles through back channels that bypassed normal production constraints. These COPO Powerglides incorporated some of Jenkins's modifications from the factory. The cases were reinforced. The clutch packs were upgraded. The converters were calibrated for higher stall speed. It was an institutional admission, delivered in the quiet language of option codes and dealer-only ordering, that Jenkins had been right. Here's something that most people outside of serious racing history circles don't realize about the financial landscape Jenkins created. Before Jenkins demonstrated the Powerglide's potential, a competitive pro-stock automatic transmission cost between $8,000 and $10,000 fully built. A Jenkins specification Powerglide cost $2,500. That price difference was not the result of inferior performance. It was the result of fewer components, simpler design, and the efficiencies that simplicity provides throughout the entire manufacturing and assembly process. The democratizing effect on the sport was immediate and substantial. Pro stock field sizes grew from 16 cars in 1970 to 64 by 1975. Weekend racers who had previously been priced out of competitive equipment suddenly had access to professional-grade drivetrain technology at a price point that didn't require factory backing or wealthy sponsors. More competitors meant more spectators. More spectators meant more sponsorship revenue. More sponsorship revenue meant better purses and more event. Jenkins's transmission choice cascaded through the entire economic structure of the sport in ways he probably didn't anticipate when he was picking transmission shrapnel out of an oil pan in late 1969. The modification industry that grew specifically around the Powerglide was, by any measure, a significant business phenomenon. By 1975, 17 separate companies were manufacturing aftermarket Powerglide components. You could order billet aluminum cases, custom gear sets machined from exotic steel alloys, carbon fiber clutch packs, electronic shift controllers, and custom torque converters designed around specific engine combinations. Jenkins sold his core modification recipe to ATI Performance Products for $50,000 in 1971, which represents the equivalent of roughly $360,000 in today's purchasing power. ATI developed a complete line they called the Super Powerglide, capable of handling 1,000 horsepower in initial trim and substantially more with further development. They sold thousands at $2,500 each. Tom Williams's transmission shop, Tom's Transmission, grew from a 2-person operation to a 30-employee facility on the strength of Powerglide work alone. Jenkins himself launched Jenkins Competition, a business dedicated to Powerglide components and complete transmissions. By 1975, that business was generating approximately $2 million annually. The man who proved the economy transmission was faster had turned that proof into a substantial commercial enterprise. Now let's examine the broader technical revolution Jenkins's Powerglide discovery set in motion, because the implications extended well beyond the specific hardware. The pro-stock Powerglide success challenged the fundamental assumption that theoretical optimization of gear ratios necessarily translated into faster elapsed times in real-world drag racing conditions. This was a significant intellectual challenge to established engineering methodology. The textbooks were correct that maintaining optimal engine RPM through the run maximized power delivery in theory. But drag racing isn't conducted in theory. It's conducted on asphalt strips with real transmissions that have real shift times, real parasitic losses, and real rotating mass that has to be accelerated from rest every single pass. Jenkins's systematic approach revealed that the gap between theoretical optimization and real-world performance could be large enough to reverse the predicted winner. The car that the formulas said should lose was winning. And rather than concluding that his measurements were wrong, Jenkins concluded that the formulas were missing variables. He found those variables, quantified them, and built a race car that accounted for them. That is fundamentally good engineering, regardless of the specific application. The reliability revelation was equally surprising to the racing establishment. TH400 transmissions were legendarily durable in street applications. They had earned their bulletproof reputation through millions of production miles in everything from half-ton pickups to police interceptors. But in pro-stock trim, running the edge of their mechanical limits every single pass, they required complete rebuilding approximately every 20 runs. The complex valve body wore through its hydraulic tolerances. The multiple clutch packs glazed under the thermal loading of repeated maximum effort launches. The 3 planetary gear sets developed clearance issues that affected shift consistency. Jenkins's rebuilt Powerglide went 50 runs between rebuilds. The math here is straightforward. Fewer components means fewer components that can wear. The simple Ravigno's gear set, with 1 sun gear, 1 planet carrier, and 1 ring gear, had dramatically fewer wear surfaces than the Simpson arrangement in the TH400. The single shift eliminated 1 complete clutch pack application cycle per run, cutting the thermal loading on the friction materials nearly in half. Jenkins ran the same transmission case for 3 complete racing seasons, which in pro stock represented well over 200 competition passes. That kind of longevity was essentially unheard of in the class. The consistency data that emerged from careful logging of Powerglide performance versus TH400 performance became one of the most compelling arguments for the simpler transmission. In bracket racing, where the objective is not to run the fastest time but to run the most consistent time, variance is the enemy. Jenkins's Powerglide setup produced run-to-run variation of less than 1/100th of a second under controlled conditions. Comparable TH400 setups, even in the hands of expert tuners, showed 3 to 4 times that variance. The single shift point, controlled electronically to the same pressure threshold every run, simply couldn't drift the way a manually shifted or governor-controlled 3-speed could. By 1975, more than 90% of bracket racers at all levels had switched to Powerglide or Powerglide-inspired 2-speed setup. Not because they were chasing Jenkins's pro-stock elapsed times, but because consistency won bracket races and the Powerglide was the most consistent automatic transmission drag racing had ever seen. The torque converter technology Jenkins pioneered with his custom high-stall units created an entirely new product category. Before Jenkins, serious racing converters were modified production units with some internal work done to address the most obvious weaknesses. Jenkins's collaboration with ATI produced converters built from purpose-designed components with no production origins at all. Furnace-brazed fins for strength. Anti-ballooning plates to prevent the converter shell from distorting under the centrifugal forces of high RPM operation. Billet steel hubs machined to exact specifications. These converters demonstrated that the production unit's design compromises were not inherent to the torque converter concept but were rather specific consequences of designing for cost and comfort rather than efficiency. The converter technology that emerged from Jenkins's Powerglide program is directly ancestral to the high-performance converters used throughout motorsport today. The $3,000 racing converter in your modern Pro Stock or Super Stock car uses design principles that trace directly back to what Jenkins and ATI worked out in Jenkins's shop in 1969 and 1970. The specific materials are different. The manufacturing tolerances are tighter. The computer modeling used in development is vastly more sophisticated. But the fundamental design philosophy, small diameter, high stall speed, tight coupling at operating RPM, anti-ballooning reinforcement, is Jenkins's philosophy. The human story running through all of this technical achievement is worth spending time with, because it provides context that the physics alone can't supply. Jenkins received hate mail. That's worth saying clearly, because it reflects how economically threatening his success was to established interests. Transmission suppliers who had invested substantially in TH400 race development programs wrote him hostile letters. Racers who had spent fortunes building 3-speed setups and developing expertise around them were not philosophically inclined to celebrate the man who had just made their investment obsolete. Some of the letters crossed from hostile into threatening. Jenkins kept a file of them, according to people who worked with him in that period, and apparently found them more amusing than frightening, which is consistent with everything else we know about his personality. But he also received letters from people at the other end of the economic spectrum. Weekend racers who had never been able to afford competitive equipment wrote to tell him that the Powerglide had opened doors for them. One letter that has been referenced in multiple historical accounts came from a disabled veteran who had lost his left leg and had believed his racing days were over. The Powerglide's 2-pedal operation, so simple that it had originally been marketed as a comfort feature for drivers who found manual transmissions burdensome, turned out to be the accessibility accommodation that let him return to competition. Jenkins's obsession with efficiency had, as a side effect, made the sport accessible to someone who had given up hope of participating. That breadth of impact, from factory engineers rethinking their most celebrated products to disabled veterans returning to their passion, is the full measure of what Jenkins accomplished by questioning a transmission nobody else thought was worth questioning. Look, Jenkins retired from driving in 1975, but he never stopped developing Powerglide technology. He continued working on transmission projects until his death in 2012, and his final project tells you something important about the kind of mind he had. In his 70s, Jenkins was developing a Powerglide with variable ratio technology. The concept was essentially a continuously variable transmission built on the Ravigno's gear set architecture, capable of delivering an infinite number of ratios between 2:1 and 1:1. It never reached production, but the prototype reportedly ran 7.50s in testing at a track in Pennsylvania. Jenkins was 76 years old, and he was still resetting the benchmark. The international dimension of Powerglide influence is often overlooked in American-centric accounts of the story. Australian drag racers were importing Jenkins-built Powerglides for their pro stock Holdens within a couple of seasons of his 1970 success, paying substantial premiums for the privilege because the performance advantage was simply too clear to ignore. Japanese teams adapted the principles to their rotary-powered RX-7 Pro stock cars. European drag racers who ran in NHRA-adjacent sanctioning bodies followed the American lead with relatively short delays. A transmission designed for 1950s American family sedans was winning drag races on multiple continents by the mid-1970s. Jenkins received correspondence from racers in 15 countries seeking guidance, and by all accounts he answered those letters personally, usually with characteristic bluntness and occasionally useful information buried inside the bluntness. Here's a detail that illuminates exactly how thoroughly Jenkins's Powerglide validation penetrated even into spaces far removed from drag racing. In the period following the Apollo program, NASA was developing the Auxiliary Power Unit System for the Space Shuttle Orbiter. The APU required a transmission capable of delivering maximum efficiency with minimum weight under demanding operational conditions and with extremely high reliability requirements. The engineering team studying transmission options was aware of Jenkins's Powerglide work through connections in the engineering community, and the simple Ravigno's gear set's efficiency characteristics were directly relevant to their design requirements. The APU gearbox that eventually flew in the Space Shuttle incorporated design principles derived from Jenkins's Powerglide analysis. Jenkins consulted on the project, reportedly earning $100,000 for 3 months of work, which represents a satisfying conclusion to the story of a man whose Junkyard transmission was once the subject of mockery in a drag racing pit lane. Now let's look at the hard numbers that define Jenkins's legacy in statistical terms, because the record speaks with a clarity that no argument can counter. Between 1970 and 1980, Powerglide-equipped cars won 73% of all NHRA Pro Stock events. They set every national elapsed time record in the class from 1971 through 1978. Warren Johnson's 7.98-second pass at the 1982 Winter Nationals, which stood as a landmark in pro stock development for its era, was powered through a Powerglide. The transmission that Chevrolet's own engineers had recommended exclusively for 6-cylinder applications and modest small-block V8s had become, within the span of a single decade, the most statistically dominant racing transmission in the history of the sport's premier class. If you were betting on drag racing in the 1970s and you faded against any car running a Powerglide, you lost money consistently enough that you would have eventually stopped doing it. The competitive dominance was comprehensive enough that sanctioning bodies briefly considered whether to restrict the Powerglide, in the same way that dominant technologies in other classes had occasionally been addressed through rule changes. Ultimately, no restriction was implemented, partly because the Powerglide's advantage derived from sound engineering rather than any specific technical violation, and partly because restricting a transmission for being too well designed would have been difficult to defend publicly. The Powerglide won because Jenkins was right about the physics, and you can't write a rule that makes physics wrong. What Jenkins identified and exploited was essentially a category error in the conventional wisdom of drag racing transmission selection. The field had been optimizing for a metric, gear ratio coverage that was real and important but not the only relevant variable. By keeping exclusive focus on gear multiplication, the conventional approach was systematically ignoring shift losses, rotating mass penalties, and converter efficiency. Jenkins's contribution was simply to add those variables to the calculation and follow the math wherever it led. The math led to a 2-speed economy transmission, and the math was right. The modern legacy of Jenkins's Powerglide insight is visible at every level of drag racing, from pro-mod to bracket racing to street-legal heads-up classes. Contemporary pro-mod Powerglide transmissions are capable of handling 4,000 horsepower or more. The basic design remains a 2-speed Ravigno's gear set with a torque converter, identical in concept to what Jenkins installed in his 1970 Vega. The materials are exotic compared to anything available in that era. CNC-machined billet aluminum cases, carbon fiber clutch packs capable of handling 500 pound-feet of torque per individual disc, valve bodies machined to tolerances of 1/1000th of an inch, shift times that have dropped to 150 milliseconds. A complete Pro Mod Powerglide costs $15,000 or more today. But the fundamental architecture has not changed. Still 2 speeds, still 1 shift, still the same core insight that Jenkins documented in his meticulous notebooks during the 1969 development process. The sport has evolved around the Powerglide rather than past it. Modern Pro Stock has moved to 5-speed Liberty transmissions, but this is less of a departure from Jenkins's philosophy than it might appear. The Liberty's first 2-gear ratios, 1.80 to 1 and 1.01 to 1, are essentially the Powerglide ratios. The additional 3 gears in the Liberty's range are overdrive ratios that engage exclusively after the car crosses the finish line, during the shutdown and return road portion of the run. During the actual competitive portion of the pass, the quarter mile itself, the Liberty is running what racers still call the Powerglide gears. The additional ratios exist to manage engine and tire loads during shutdown, not to accelerate the car faster. Jenkins's core gear ratio selection is preserved inside the most sophisticated transmission the class has ever seen. The Tesla comparison might seem like a stretch, but it's actually quite direct. When Tesla's engineering team was developing the drivetrain architecture for the Model S Plaid, one of the key decisions was transmission configuration. Early Model S cars had experimented with a 2-speed gearbox and found significant reliability challenges. The eventual decision was single-speed direct drive, eliminating the transmission entirely for the competitive launch version. When Tesla engineers have discussed the single-speed decision publicly, they have referenced drag racing as a demonstration that fewer gear changes can produce faster elapsed times. The Powerglide principle, that the cost of shifting can exceed the benefit of additional gear multiplication, informs the drivetrain architecture of the quickest accelerating production car ever built. Jenkins's insight from a Pennsylvania garage in 1969 is, in a real and traceable way, present in a technology that didn't exist until 40 years after he first demonstrated it. This is where it gets really interesting from a historical perspective. The Powerglide story is not really a story about a transmission. It's a story about what happens when someone applies genuine intellectual rigor to a question that everyone else has decided is already answered. The transmission itself was merely the subject of the analysis. The real innovation was the analytical framework Jenkins brought to bear. He identified the right variables. He quantified them accurately. He designed solutions that addressed the actual constraints rather than the assumed ones. And he had the specific kind of stubbornness that refuses to abandon a theoretically sound approach simply because the first 3 experimental units shatter into pieces. Now, you might be thinking that Jenkins had some unique advantage in terms of resources or connections that made this possible for him in ways it wouldn't be for others. Look, the honest answer is that he had less resources than virtually every team he was competing against. He had fewer people, less money, no factory backing, and no corporate infrastructure. His advantage was methodological. He asked a different question and then actually went to the trouble of answering it with data rather than assumptions. The lesson that most people take from drag racing history is that more power wins races. More cubic inches, more boost, more airflow, and more power is never a disadvantage, obviously. But Jenkins demonstrated that the delivery system for that power matters as much as the power itself, and that optimizing the delivery system with genuine rigor can overcome substantial power deficits. His 331 cubic inch engine beat 450 cubic inch engines because the power it made was delivered to the wheels more efficiently. His $2,500 transmission beat $10,000 transmissions because the simpler design eliminated losses that the expensive design was incurring. That principle generalizes well beyond drag racing. In any system where energy is converted and transferred through multiple stages, the efficiency of each stage compounds. Losses at one stage reduce the energy available at the next. Jenkins was optimizing the entire energy transfer chain from engine to rear wheels, not just the most obvious and glamorous component of that chain. Here's what most people don't realize about Jenkins's long-term impact on the sports culture. Before his Powerglide breakthrough, the dominant assumption in drag racing's technical community was that factory programs and their associated budgets were the primary source of significant innovation. Independent racers could execute well, could drive brilliantly, could squeeze maximum performance from existing combinations, but the fundamentally new ideas came from corporate engineering departments with resources that independent operations couldn't match. Jenkins broke that assumption so completely and publicly that it permanently changed the culture of the sport. After 1970, the independent racer's ability to outthink the factory became a genuine expectation rather than an occasional surprise. The entire tradition of independently developed racing technology that defines so much of what's interesting about motorsport at every level was strengthened significantly by Jenkins's demonstration that rigorous independent analysis could find things that corporate programs missed. The economic democratization that followed, the drop in competitive drivetrain costs, the growth in field sizes, the broader participation at every level, all of that traces back to one guy who was willing to bolt a grandmother's transmission into a pro stock car and stand behind his math when everyone in the paddock laughed at him. Bill Jenkins died in 2012 at the age of 77. His obituaries in the racing press focused appropriately on his achievements as a driver and engine builder, because those achievements were substantial and well documented. But the Powerglide story may ultimately be his most lasting contribution, not because it produced the most wins or the most records, though it produced plenty of both, but because it demonstrated something important about how progress happens. Progress doesn't always arrive from the direction you're looking. Sometimes the transmission everyone threw away is the right transmission. Sometimes the question everyone stopped asking is the one that changes everything. Sometimes the grumpy guy in the two-bay garage is doing better physics than the engineers in the corporate facility, not because he has better tools, but because he's willing to follow the numbers wherever they lead without regard for whether the answer is convenient or comfortable or consistent with what everyone already believes. Jenkins followed the numbers to a Powerglide. The numbers were correct, and drag racing has been different ever since. The next time you're watching a run where a car launches off the line and you hear that distinctive mechanical event at half-track, that moment where everything changes and the car just pulls harder toward the stripe, think about what that single shift represents. It represents 50 years of refinement of an insight that originated in Bill Jenkins's obsessive analysis of a transmission everyone else had discarded. It represents the decision to question what everyone assumed was settled. It represents the competitive advantage that comes from asking the question that nobody else thought was worth asking. Not bad for a grocery-getter transmission. What's the most unconventional modification or equipment choice you've ever seen actually deliver real performance in racing or in any mechanical application you've encountered? Drop it in the comments because this community has seen things that would surprise everyone, and the best stories down there are genuinely worth reading. If this kind of deep technical storytelling about the people and decisions that changed motorsports history is what you're here for, the subscribe button is right there, and it costs you nothing. Every video on this channel goes this deep. We don't do surface-level content here. Until next time, keep questioning the assumptions that everyone around you has stopped questioning. The answer that changes everything might be sitting in a junkyard right now, waiting for someone stubborn enough to pick it up.